Ladies and gentlemen, welcome. My name is Daniel Gonzalez, and this is the 38th installment of the scheduling seminar. First of all, let me ask Mike Pinedo to introduce the speaker.
Okay, our speaker today is, as you can see from the PowerPoint, Professor Hyun-Jung Kim from KAIST. All of you know KAIST. It's the MIT of Korea. Probably KAIST say that MIT is the KAIST of the United States. She is, as a good engineering school professor, she of course she got all her degrees at KAIST, a bachelor's, master's, PhD. She's not a professor, and she has, of course, as a good engineering school professor, her own lab. I think it's called the Manufacturing and Service Systems Lab. And I just went to their website. You should go to their homepage of her lab. She has only 7 PhD students, which I cannot understand how a person can handle 7 PhD students. But and she knows a lot about scheduling, and she knows a lot about machine learning, and she knows also a lot about practice, because as a good Korean, she has her connections with Samsung and all the big Korean companies. So, okay, Hyun-Jung, I'm very happy that you're here. You can start.
Okay, so thank you for the introduction. Hello, I'm Hyun-Jung Kim from KAIST in Korea, and thank you for inviting me to this scheduling seminar. Today, I want to talk about scheduling with machine learning. Recently, a lot of manufacturing companies and researchers are interested in applying machine learning approach for scheduling problems. So I want to introduce various applications of scheduling problems where machine learning can be applied. So most of the applications are from semiconductor manufacturing, but I will also introduce scheduling problems for steel manufacturing and insulation manufacturing and some other industrial scheduling problems. Yeah, so scheduling, I believe you're all familiar with the definition of scheduling. So scheduling is the field of study concerned with optimal allocation of resources over time to a set of tasks. So here the resources and tasks depend on the situations. In manufacturing, resources are workers or machines, and tasks are jobs or operations of jobs. And there are a lot of applications of scheduling problems, especially like from semiconductor, LCD, steel, automotive, battery, biopharmaceutical, and so on. And machine learning approaches have been used for scheduling in manufacturing. So today I want to introduce various examples. This photo shows you the semiconductor manufacturing fab, which consists of hundreds of machines and hundreds of OHTs, which transport wafer cassettes between machines. Here you can see the wafer cassettes, which typically contains 25 wafers. So wafer cassettes can be considered to be jobs in semiconductor manufacturing scheduling problems. So they need to visit a lot of machines, basically a lot of process steps. And OHTs here transport wafer cassettes between machines. And this, you can see the simplified layout of the semiconductor manufacturing fab. Here, the gray boxes indicate machines, and you can see the OHTs here. And then you can also see the stockers, which store wafer cassettes. So first, I want to talk about scheduling problems for semiconductor manufacturing. So I think we can find 2 types of scheduling problems in semiconductor manufacturing. The first one is the production scheduling or fab scheduling. The second one is the tool scheduling. So in here production scheduling, basically there are a lot of different types of jobs or wafer cassettes, and they need to visit, for example, one of machines in stage 1, and then one of machines in stage 2, one of machines in stage 3, and so on. And then they also need to revisit some machines again. So fab scheduling for semiconductor manufacturing can be seen as like flexible jobs with reentrant flows. And of course, there are a lot of complicated constraints. You might need to consider sequence-dependent setup times. You might need to consider time window constraints. You might need to think about machine dedication and so on. And also the tool scheduling, if you take a look at the inside of the machine here, this machine here, you can actually see wafer cassettes are loaded here. If you take a look at the inside of the tool, it looks like this. So when wafer cassettes with 25 wafers arrive at the load lock here, there is a material handling robot. So this robot unloads one wafer, transports it, and loads it into one of processing modules. And when a process in this processing module is finished, this robot again transports this wafer to another processing module. And also here you can see the wet station, which is used for cleaning wafers. So when jobs arrive here, and you can see the multiple robots, and each can move only within the given range. So when jobs arrive here, this robot can move the job to this machine. And when the process in this machine is finished, this robot can move this job to either this or this machine. And when a process in this machine is finished, this robot can move this job to either this or this machine. So things like that. So tool scheduling is basically to determine the robot task sequence instead of sequencing jobs. So once you determine the robot task sequence, we can actually have a complete schedule, and the robot task sequence affects the throughput. So I want to talk about these two scheduling problems, production scheduling and tool scheduling, but mostly I want to focus on production scheduling problems with machine learning. So since the production environment in semiconductor manufacturing is dynamic, they often use dispatching rules, right? When there are multiple machines and when a machine it becomes idle, we need to select one of jobs in the buffer to assign the job to the corresponding machine. In that case, engineers use dispatching rules, for example, like a shortest processing time or longest processing time, earliest due date, and so on. By using these dispatching rules, they select one job and assign the job to the corresponding machine. I actually saw there were like 40 dispatching rules in one of largest semiconductor manufacturing companies in Korea. Of course, they don't use just one dispatching rule. They want to use multiple dispatching rules simultaneously. So when there are n dispatching rules, they basically assign weight for each dispatching rule. And then they compute the weighted sum and then select the job that has the largest value. That's how they actually use multiple dispatching rules at the same time. So the weights can range from 1 and 100,000. Of course, it can be larger than that. Then, of course, the question here is that what is the best or optimal weight set? For example, we want to use 3 dispatching rules, in this case, SPT, LPT, EDD, then is it optimal to assign like 1, 10, and 100 for each dispatching rule, or 10, 10, 100? So engineers want to know what is the best or optimal weight set. In this case, this problem can be solved with a machine learning approach. Well, we actually received the real data, but the problem was that the real data did not have much information because engineers are actually reluctant to modify the given weight set significantly because it can cause some problems. So the real data did not have much information. So we had to generate data to apply the machine learning approach. So we were able to generate data by using simulator, which was developed by one of software companies in Korea. So the company has a simulation-based scheduler, and that scheduler actually was used by the semiconductor manufacturing fabs. So we were able to use that simulator, and then we were able to generate data. So to generate data, we first need to sample some weight sets, and then we obtained KPI. In this case, KPI can be like throughput. It can be the sum of setup times. So those objective values can be obtained with the simulation. And then once we have the data, we can actually analyze the relationship between dispatching rule weights and KPI. And with the data, we can derive the good model, which can actually represent the relationship between the dispatching rule weight sets and the KPI. And once we have this model, we can actually suggest a good weight set. That was the one project that I had. And another case here I want to introduce is basically still we want to obtain the weight sets for multiple dispatching rules. But in the previous slide, we were able to generate some data. But what if we don't have enough time to generate data? So what if we are given just a short time, like we are given 1 hour or we are given 3 hours. So within 1 hour, please derive a good weight set for scheduling of semiconductor manufacturing. So those kind of problems should be considered in practice. So in that case, let's assume that we are given like 1 hour, and let's assume that it takes 1 minute to compute the KPI for a given weight set. Then we can actually evaluate 60 weight sets, right, with the simulation, because it takes 1 minute for each weight set. So then we can, so within like 1 hour, we can generate 60 weight sets, and we can evaluate the KPIs for 60 weight sets, and then we can actually select the best one among the 60. So in that case, we derive the procedure, which consists of here the 6 steps. So let's assume we have 2 dispatching rules. Okay, so x-axis indicates the weight of dispatching rule 1, and y-axis indicates the weight of dispatching rule 2. And at the beginning, we just sample a small number of weight sets, in this case, like 5. Okay, so and then we evaluate, we compute the KPI with the simulation for the 5 weight sets. And then by using this information, we divide the search space, and then we remain only the promising areas and eliminate other areas. And then we sample more data points from promising areas. Again, evaluate the KPI values with the simulation. So at the beginning, we had 5 samples, but now we have like 10 samples. And then with 10 samples, we again divide the search space and remain the promising areas and sample more data points, evaluate the KPI values again and again. So we repeat these procedures until the given number of sample data weight sets that we can actually evaluate. That was another procedure that we developed and we had with the company. So in this case, we can, of course, use the machine learning approach. So in practice, engineers want to use multiple dispatching rules simultaneously. To do that, they need to have weights. So we actually developed some approaches to propose a good weight set, but still it is very challenging to develop or propose a good weight set. So what if we can actually design a very sophisticated dispatching rule, which considers not only processing times, due dates, but also like remaining operations and remaining processing times. So we don't want to use a simple dispatching rule because the performance is not good. So SPT, LPT only considers processing times, like EDD only considers due dates. But what if we can actually design a sophisticated dispatching rule, which considers a lot of things? So reinforcement learning has recently applied for scheduling problems, especially here, the job scheduling problem, which you can find in semiconductor manufacturing. So you might be familiar with the reinforcement learning. So let me briefly talk about, explain that. So there is an agent. So agent observes the state, and then it selects an action. and then receives the reward. So based on the reward, it learns the best action, right? So in the scheduling perspective, there is a scheduler, which can be an agent, and then the scheduler observes the state. So then state, in this case, you need to define that. State can be like a processing times of jobs in the buffer. States can be like a remaining operations of those jobs in the buffer, or remaining processing times of jobs in the buffer, kind of thing. And then by observing the state, the agent selects an action. So in this case, action can be to select one job in the buffer. Okay, that can be the action. And the rewards, it depends on the objective value you use. If you use the make span, the reward can be like a state transition time, or reward can be the idle time in the bottling machine, or it can be also other things. So reinforcement learning basically here tries to derive a very good, sophisticated dispatching rule, actually. So let's take a look at this example. So there are 3 jobs and 3 machines. And here OIJ indicates the jth operation of job I. So at this point, let's assume that at this point, here the machine 1 becomes idle. Then jobs 2 and 1 are in the buffer. So then agent observes the state. Maybe it will take a look at the processing times of this operation and processing time of this operation in machine 1, and it will also consider the remaining processing, remaining operation of job 2, and also maybe its processing time as well. And then the agent will select the best job, in this case, job 2, and then it will receive the reward, right? So with the reinforcement learning, we can actually derive such a complicated and sophisticated dispatching rule. And we also know that job shop scheduling problem is well represented with this disjunctive graph, right? So at the beginning, we haven't determined the operation sequence in each machine. That's why here you can see the pairs of disjunctive arcs, right? So basically there are 3 jobs. Okay, so job 1 has 3 operations, job 2 has 2 operations, and job 3 has 3 operations. And colors here, the same colors are operations that are conducted in the same machine, right? And once we determine the sequence of jobs in each machine, we can actually select one disjunctive arc from each pair, right? So the action can also be to select only one disjunctive arc from each pair, okay? So, but the problem with the reinforcement learning is that the agent does not have much information at the beginning. So it tries a lot of different actions. So it takes a long time to train the agent. So we can actually use supervised learning. So here, the supervised learning means that we can actually obtain optimal solutions or good solutions for small-sized instances for job scheduling problems. Then, in the optimal schedules, at each decision point, so here the decision point means whenever a machine becomes idle, we can actually observe the state, and then we can actually see the job that is actually assigned in the optimal schedule. So we just store those data into the data set, and then we can learn the agent by using this data set, like a supervised learning. In that case, we can actually improve the performance further. So I'm not going to explain the details of the reinforcement learning for job scheduling problem, but a lot of researchers have tried to apply the reinforcement learning for not only the job scheduling problem, but also like a flexible job shop, flexible flow shop, and parallel machine scheduling problem. And I think with the reinforcement learning, we can get a good dispatching rule, which can actually represent multiple dispatching rules. So far I have talked about the production scheduling, the fab scheduling, and now I want to briefly talk about the tool scheduling. So if you take a look at the inside machine, the semiconductor manufacturing machine, then it looks like this. So there is a transport robot. So this tool is called a single-armed cluster tool, and this tool is called dual-armed cluster tool. So it consists of multiple processing models here, and then the one material handling robot and load locks, where wafer cassettes are loaded or unloaded. And wafers need to be processed in processing modules in sequence, but some wafers might need to be processed on PM1, PM2, PM3, and PM4, while others might need to be processed in PM1, PM2, and PM4. And also there can be like a reentrant flows like PM1, PM2, PM3, and then PM2, PM3. And there can be also time window constraints. So it can have diverse wafer flows. It can have a lot of complicated scheduling constraints. So the cluster scheduling problem is to determine the robot task sequence. So for example, there is wafer 1 in PM4, and there is wafer 2 in PM2, and there is wafer 3 in the load lock. In this case, the robot can need to choose one of 3 tasks, whether it just goes to PM4 and then moves it to the load lock, or it goes to PM2 and moves wafer 2, or it goes to load lock and moves the wafer. So among the 3 tasks, the robot need to choose one task, and this robot task sequence actually determines the complete schedule, and it affects the throughput of the cluster tools. And there have been numerous papers on cluster tool scheduling problems, and many of them analyze the cyclic scheduling by assuming identical wafers, which have the same wafer flow and same processing times in each PM. So you can see many theoretical results from those papers. But recently, due to the larger wafer size and circuit width reduction, sometimes we need to operate the tool non-cyclically, in a non-cyclic manner, because we need to produce different wafer types concurrently or consecutively. So in that case, it is hard to operate cluster tools in a cyclic manner. I think in such a case, reinforcement learning can be very useful. So of course, if we can assume cyclic scheduling with identical wafers, we don't need to use reinforcement learning. But when we need to operate the tools in a non-cyclic manner with many different types of wafers, I think reinforcement learning can provide the good dispatching rule. Yeah. So these are the scheduling problems that I wanted to talk about from the semiconductor manufacturing. And now I want to talk about the scheduling problem from steel manufacturing. Steel manufacturing consists of like here raw materials preparation step, iron making step, steel making step, continuous casting step, and so on. And I want to focus on here steel making step. So in the iron making step, we obtain molten iron from raw materials, and molten iron is transported to steel making step, and then some impurities are removed and alloying elements are added in the steel making step. So let's take a look at the steel making process in detail. So basically, there are 3 stages: stage 1, stage 2, and stage 3. And stage 3 is just a continuous casting process step. And stage 1, there are multiple converters, and stage 2, there are multiple machines for RH and LF, and of course there are multiple machines for continuous casting. So when molten iron arrives, they are called jobs, or they are called charges. So when charges arrives, the engineers assign each charge or each job to one of the machines in stage 2. Okay? And then, but the engineers also assigned cranes. So there are cranes that transport here the charges between converter and RH. And also there are cranes that transport charges between RH and the continuous casting process step. So engineers need to assign jobs to one of the RH machines, but they also need to assign the cranes. They also need to assign some other like ladles, which contain the molten iron. So they do a lot of things simultaneously. So here we try to assist engineers. So we wanted to develop a good approach for the assignment of jobs to here the one of machines in stage 2. That's actually kind of parallel machine scheduling problem. And in this case, the actually is all jobs need to visit one of machines, one of RH machines, but some jobs need to visit both RH and LF machines. But the company we worked with had only like one LF machine, so we don't need to think about the assignment for the LF machine. We only need to think about the assignment of RH machines. Okay, so at the beginning, we actually thought about 2 approaches: mathematical programming model, mixed integer linear programming model, and then the machine learning approach. So both have like a pros and cons. So if you just use the mathematical programming model, you can actually obtain an optimal assignment, right? But then the problem was that engineers have their own preferences, which cannot be modeled mathematically. So if you obtain an optimal solution from the MILP model, the results were quite different from what engineers have been assigned. Okay? If you use the machine learning approach, we can actually derive the similar results from the engineers. But the problem here is that the performance cannot be increased, right? So it cannot outperform the engineers. So in this case, we try to combine these 2 methods, MILP and machine learning approach. So I will talk about this. So I want to first talk about the mathematical programming model. So we first need to define the objective function. So we talked about this objective function with engineers, and then we determined to maximize the average time each charge or each job spends between RH and CC. So here the completion time in RH and the start time in CC. Here we want to maximize this average time. So here the red arcs here indicate the time related to the objective function. And then here blue arcs, arrows indicate the transportation time. So basically after completing the process in RH, the charge need to wait for the crane, and the crane will transport the charge to continuous casting caster, and that it needs to wait until the start time. Okay, so we want to maximize the average time each job spends between RH and CC. So this is the reason for choosing this objective function. So basically the start time in continuous casting step is given. It is determined by continuous casting engineers. But if we can maximize this time, we can actually talk about this with continuous casting engineers and persuade them to set the start time earlier than this. That's why we chose this objective function. To solve this assignment problem with this objective function, we defined some decision variables. I'm not going to explain them in detail. We had some decision variable for allocation and the start time and so on. And we derived some constraints. Of course, all jobs need to visit first converter and then one of RH machines and then the CC, continuous casting. And of course, one machine can process one job at a time, and those kind of constraints are added. And also we considered some special features there. Some high quality charges cannot be assigned to the machine, remained idle longer than some duration, and some special charges cannot be assigned consecutively to the same machine, and those kind of constraints are added as well. So with this MILP model, we can obtain an optimal assignment problem. And now I want to talk about the machine learning approach. So this is the example of the real data. Here you can see the types, the job types, and you can see the converter number, which is assigned. And you can also see the continuous caster number. And you can also see the second refining code, which actually indicates a set of candidate machines that can be assigned. And this is the result, the assignment that we need to derive. And you can also see the start and end time for each stage, stage 1, stage 2, and stage 3. And so these are the assignment that already assigned here. And here we need to derive this, the assignment, for like job 11. Okay. So to use the machine learning approach, we first need to extract some features, right, by considering the characteristics of charges and the machines. So we use some like whether that charge or that job is special charge or just a normal charge, or whether it requires like a low carbon or not. And also we use the second refining code. We also use the converter and continuous caster number assigned, and those kind of features were used. Once we have features and we have the assignment result from the engineers, we were able to apply the machine learning approach to derive the model. So that the output of the model will be the whether it is the first RH machine or second RH machine or third RH machine, that. So if we use the some machine learning approach, we can actually, we were able to derive the accuracy larger than 90%. So with the accuracy larger than 90%, engineers were very satisfied with that. They said they can actually use that model. But as I mentioned, if you just try to follow the engineer's decisions, you cannot outperform the engineer's assignments. So here we try to combine the MILP model and the machine learning model. So this is the procedure. We basically use the result from the machine learning model, because if you just use the MILP model, as I mentioned, the result is quite different. So engineers will not use the proposed approach, proposed method. So basically it follows the result from the machine learning approach. But if the result is not reliable, in that case, we run the MILP model. So here the reliable means that with the machine learning approach, we actually get the assignment probability for each machine as the output. And we choose the machine that has the largest probability. So if the probability is larger than 90% for a certain machine, then we can actually say that, yeah, it is quite reliable. But if the probability, the largest probability is only like a 60%, then we may not be able to say like it is reliable. So in that case, we run the MILP model and use the result from the MILP model. And then we developed a simulation and then tested this approach. And this graph shows the result. The x-axis indicates the machine learning coverage. So 1 means that we use the result only from the machine learning approach. And then 0.9 means that 90% from the machine learning approach and 10% result from the MILP model. And 80% here from machine learning and 20% from MILP model. And the y-axis indicates the objective value. And I mentioned we want to maximize the time, so the larger is the better. And of course, as we decrease the machine learning coverage, the objective value increases, right? Because we, if you use the MILP model, we can actually maximize the time, right? So we can actually improve the performance as we decrease the machine learning coverage. But the problem, as I mentioned, the result is quite different what engineers have been done. So we talked about this with engineers, and we decided to use around at this point. So 80% from machine learning approach and 20% from the MILP model. So that was the project that I had with one of companies in Korea. And now I want to briefly talk about the insulation manufacturing as well. Here, this is the insulation. So insulation is used inside window frames to keep the house warm. And we first mix some ingredients, and then the mixture is fed into a board in the forming step, and then it is hardened in the curing step, and it is cut in the cutting step. So there are three process steps: forming, curing, cutting. So it is, and also since it takes a long time in the curing process, so the company we worked with had multiple machines in stage 2, but only one machine for stage 1 and one machine for stage 3. So it is a hybrid flow shop scheduling problem. And there are some special constraints, like there is no waiting time between stage 1 and stage 2, and there is no buffer between stage 2 and stage 3. So there is basically blocking. Okay? So that's the problem. This is the scheduling problem they had in insulation manufacturing, and they were interested in tardiness and mixed measures. So you can apply many different scheduling algorithms. You can use meta heuristics, and you can use other scheduling algorithms for this problem. We actually use the NH-based algorithm. So NH is very easy to understand, easy to explain, easy to implement, and I believe you are all familiar with NH algorithm, but let me briefly talk about that. So for the NH algorithm, we first need to order jobs. So here the O means orders, but you can just think of it as jobs. So we first need to order jobs, right, by using based on any other like a standard. And then you first need to select the first job and then put it here. And then we select the next job and then put it either here, like before job 1 or after job 1, and select the best one. So let's assume that this is the best one. Okay. And then we select the next one and then put it either here or here, here, and then select the best one again. Okay, so that's the NH algorithm. I think the NH algorithm has two issues. The first one is that the performance of the NH algorithm depends on the initial ordering here. How you actually order the jobs at the beginning, that affects performance. And also, it selects partial schedules greedily, right? So it might be good to overcome these two issues. And I think the second issue can be addressed by having multiple solutions instead of just one solution. So we have like a first job here, O1, and then in the second step, we need to select the O3 and then put it either here or here. So in the basic NEH, we only select the best partial schedule, in this case, this one, right? But we can also carry like a multiple solutions, right? We don't need to eliminate this. We can just keep some solutions. And then in the next step, we take the O4 and then put it either here, here, here. And of course, for this, we need to put either here, here, here. And then we can generate more schedules. And of course, in this case, we can keep some multiple solutions. In that case, I think we can handle the second issue, but I want to actually talk about the first issue. The performance of the NH algorithm depends on how you order the jobs at the beginning. And also the ordering rule should be different depending on a set of jobs that you have, the characteristics of those jobs, right? So I thought in this case, we might be able to use the machine learning approach. So for the initial ordering here rule. So we had to generate a week schedule. So we usually have like 22 or 20 to 30 jobs or orders. And then here we derive the features like due dates of those orders, or processing times, or the factory state, or some other features. And then we tested with many different ordering rules, like EDD or LPT or some other rules. And then we can actually generate data, and then we can actually train a decision tree in this case. Of course, you can use other machine learning approach, but we chose decision tree because we can actually explain the result. So with this decision tree, when you are given a set of orders or a set of jobs, you can actually select the best ordering rule you can use. So this decision tree provides you the best ordering rule you can use for the NH algorithm. So in that case, you don't need to use one ordering rule for all the jobs that you need to schedule. So, and of course, you can improve the performance compared to the basic NH algorithm. So that was the machine learning approach we used for, in this case, the hybrid flow chart scheduling with NH algorithm. So the last one that I want to briefly talk about here is the project scheduling for shipbuilding. Resource constraint project scheduling problem is very general and a well-known scheduling problem. And in this case, of course, the reinforcement learning can be used. But another issue that is very important in project scheduling problem is resource leveling. So here, so once you have a schedule, okay, once you have a schedule, it is very important to have the to have the constant resource level. So especially for the shipbuilding area, here the resources usually indicate the workers. So once you have an initial schedule, you can actually derive the number of workers you need to have for each week or for each month. And of course, it is very important to have the constant level of workers so that you can minimize the cost, right? So in one of the companies in Korea, the engineers actually manually adjust the start time of each task so that they can have the constant level of here the resources. And we actually applied the reinforcement learning for this problem. And here you can see the x-axis indicates the time and y-axis indicates the resource level. And then the here red bars are the real resource level obtained from the real data. And then blue bars are the ones that derived from our approach. So we were able to reduce the peak resource level here. So, so far I have introduced the many applications of scheduling problems where machine learning can be applied. So, whenever I want to implement my algorithm into real manufacturing systems, there are some obstacles. And one of them is explainability, actually. So engineers want to know why such a schedule is derived and how such a schedule is derived and why a specific job is assigned at this point. Those kind of explainability, they actually require that. So I actually wanted to introduce this paper. It was published in 2010. So the objective of this paper was to learn dispatching rule from optimal scheduling data. So not for like explainability. It was trying to extract dispatching rule from optimal scheduling data, but I think we can use this framework for explaining the scheduling results. So basically, we generate the schedules, right? By using machine learning or some complicated algorithms, we can generate good schedules, right? And then we can generate a training data set from good schedules. And then we learn a decision tree. Then we can actually explain the scheduling result. Then how can you actually generate a training data set? So in the paper, they compare each pair of jobs, okay, all pairs of jobs. So for example, these are the features, and this can be the Y variable. So whether the job 1's processing time is larger than job 2's processing time, whether job 1's tail processing time is larger than job 2's tail processing time, and those kind of features are used. And then the Y variable here, though, whether job 1 goes first or job 2 goes first. So if job 1 goes first, we put like true, otherwise false. So we generate the training data set from the good schedules. And then by using this data set, we can train a decision tree. Then we can actually explain. Of course, it may not be perfect, but we can at least explain a little bit by using this one. And I think it would be a good research topic for the explainability of the scheduling result. So yeah, almost done. I have explained the scheduling with machine learning, but of course, for simple, small, and deterministic scheduling problems, it would be good to use optimization algorithms and mathematical analysis. But the machine learning-based scheduling is good for complex and large manufacturing systems with random variability and disruptions. As I mentioned, reinforcement learning can design a very sophisticated dispatching rule. So this table compares the exact algorithm, meta-heuristics, dispatching rule, and machine learning-based approach. And of course, performance, we can obtain an optimal solution with exact algorithm. Meta-heuristic, of course, the performance is quite good. If you use just a simple dispatching rule, the performance might not be good. Machine learning, we don't know yet, but if you take a look at the research papers, they claim that of course, it outperforms the dispatching rules. And sometimes it says that the result is very close to the meta-heuristics. But exact algorithms and meta-heuristics, it is very hard to use them for real-time scheduling or in dynamic environment. But dispatching rule and machine learning approach are very appropriate in those situations. And also in scheduling area, the timing control is also very important. Depending on depending on the starting time of each task, the schedule can be infeasible when you especially consider like time window constraints. So dispatching rule cannot handle that. Machine learning, I'm not sure. So we need to work on the timing control for scheduling with machine learning further. So as a result, machine learning is very useful tool, and I think you can use the machine learning, especially when you schedule in a dynamic environment. Okay, so yeah, thank you for listening. I have introduced many applications. So if you have any question, feel free to ask me.
Okay, thank you very much. And I would like to ask the audience to ask questions or share their views. So I have allowed you to unmute your microphone, so don't hesitate and go ahead if there is a question.
Can I ask a question?
Hello. Yeah.
Hi. Can I ask a question?
Yeah. Go ahead.
First of all, thank you very much for this, interesting presentation. It's just sort of a hot topic, machine learning, and it's always a big question that how we can, take advantage of machine learning. I like it a lot, especially in slide number 24. But I have a couple of questions based on, I was in academia and then, working in practice. In all your present, real world practices that you presented, I guess only for one of them, you did not talk about the objective function. So in the flexible flowchart problem, you only mentioned that the minimization of make span was the objective, but for the rest, you did not emphasize on that, which I believe that is very important, and then, so I believe that even if we use machine learning in order to find some rules for it, even say for example, a simple job shop problem with minimization of make span. I guess we cannot use those rules if the objective is changed, right? Because it's just totally different, so you cannot use that one. So that's one challenge that I would like to ask you, that how do you, handle that? Because usually companies are looking for different objectives in different cases, so we cannot use one of them and then, suggest for the rest of, objective functions. The other thing that I learned that for, job shop and flow shop problems, so by having different schedules, the bottlenecks are changing. So, for example, if you have a very bad schedule, so non-bottleneck machines might turn to be a bottleneck because they starve a lot. So then that might be a problem. So usually my interest was just, okay, how we can, find how the bottlenecks are shifted by different schedules. So can we, is there any research available? So maybe it can address, your problem as well. Just for focusing on job sequence, find out, okay, how the bottlenecks are shifting. And then if we can handle them, we can come up with a better sequence. So what do you think that, for the, just finding the bottlenecks based on changing the sequence of processing the jobs?
Yeah, thank you for the question. About the first question, yeah, here I talked about the objective function tardiness and expand. They were interested in tardiness and expand. So in this steel manufacturing, in this case, yeah, objective function was to maximize the average time each charge spans between here the RH and CC. And then for the semiconductor manufacturing, mostly here, yeah. So in this case, actually, engineers were wanted to use multiple objectives, not the single objective. They wanted to use like a throughput, and they wanted to use the sum of setup times, and they also wanted to use the due date related objective function. So the multiple objective function. So actually, we were trying to develop Pareto optimal solutions for those multi-objective functions. But anyway, for a single objective function, this is just a framework that we suggest, of course, for this one as well. So even if the objective function is different, we can just follow the same procedure. Then we can actually derive the good resets, of course. And for the here's the job shop scheduling problem. Of course, if the reinforcement learning, the agent learns very good dispatcher rule with the make span measure, then it may not be able to use it for another objective function, right? Because we need to run the agent again for another objective function. So that's why recently, as far as I know, there is a meta learning or transfer learning, so that once you learn an agent, and then you can easily modify or a little bit, you just do a little bit of tuning to learn the agent for another objective function in a very short time. So that's maybe one research area that you might want to take a look at. And then about the second question, bottleneck is changing, and I know that the bottleneck is changing. I know that's very, very challenging research issue in practice. There's no exact answer to do that, and I'm not sure whether there is. Yeah, I think there is a paper about the issue that you mentioned in the second question, and yeah, it is very hard to do that. You just need to use some like a simulation, or you can use some digital twin, this kind of thing, and then you might need to analyze the number of jobs in each buffer. You might need to calculate the utilization of machines from time to time, and then try to detect the bottleneck. Yeah.
Yes, thank you. Exactly. I use simulation to find this. So my question was that can we take advantage of machine learning to just, tackle that problem? Do what do you think based on your experience?
Yeah, I think, of course, you can do that. So I did not introduce in this seminar, but I had another project with one of semiconductor manufacturing companies. It was about the setup change issue. So the engineers need to determine when they actually change the setups for each machine. Because it takes a long time once you actually do the setup for each machine. So in that case, they need to consider the jobs that will arrive in the future. So in that case, they can use the simulation, but simulation takes a long time.
Right.
So yeah, you can actually, in that case, use the machine learning to predict so how many jobs will arrive in the future. So I think you can use the machine learning to detect the bottleneck. Of course, it is challenging, but I think you can try.
Let me ask you a related question, actually. Can you go back to your slide 13? You say here that you want to maximize the red arrows there, the average time, the average waiting time. I would have suspected, and I've also spoken with people in the steel industry, that actually, well, you have that the transportation time, which is a minimum time that has to wait, but actually you want to minimize the average waiting time, because if they wait along, the temperature will, the steel will cool down, and you have to do reheating, which your electricity bill, which is the most important part of the steel making process, your electricity bill goes up. So actually you want to, I would have said, hey, listen, the blue arrow there is sort of a constraint. You have to take care of the transportation time. But the red arrow, you want to have the length of the red arrow to be actually only slightly larger than the blue arrow, because you don't want the steel to cool down. How come that you say here that you want to maximize the average time each charge spans between RH, ILF, and the continuous caster? I'm a little bit surprised by that.
Yes, thank you for the question. We talked about the objective functions a lot with engineers. And then I think the purpose is a little bit different. So start time in the continuous casting process is given. It is determined by the continuous casting engineers, okay? But if we can actually maximize this time, then we can actually talk about this. So we means that steelmaking engineers can talk about this with continuous casting engineers and persuade them to set up the start time earlier than this.
Oh, so they are, okay,
yes.
Okay.
Yeah, then in that case, we can actually improve the productivity. So that's what they wanted to do. Yeah.
Okay, thank you. Okay, there
Right.
is what is Panafotis?
Panayotis. Hi, Zdenek. Long time no see.
Yeah, hello. Go ahead.
Yes. So we're in a research project that is very similar. We are also working with it seems interesting that we are also working with very high energy consumption industries like you right now in a very large European project. And what we found out is that what is more important for the scheduling of the wafer production is that, unfortunately, this problem is extremely long term. It takes about a month or more to process all 500 steps. So what do you think is important to use? Why do you think it's important to use machine learning, given that the scheduling horizon is extremely long? A job takes more than a month, and there are 500 steps that are recurring again and again. So why don't we use some kind of real scheduling algorithm? I think machine learning is very good at dispatching. I agree, but we want to plan ahead. This is an extremely costly process. We cannot just hope for just some dispatching that you have enough.
Yeah, thank you for the question.
Sorry.
Yeah, so it is very complicated in I know it takes 1 month or 2 months to complete all the processes in semiconductor manufacturing. So there are basically 2 levels: production planning level, and then the scheduling and dispatching level. So once you have the production plan, we need to do the scheduling, right? So, and the scheduling problems that I introduced are actually the real-time scheduling. So since there are hundreds of machines, hundreds of OHTs, and a lot of wafer cassettes, we need to assign the wafer cassettes to machines in real time, right? So in that case, we can just use the dispatching rules, as I mentioned, like a combined dispatching rules with weights. But then the performance of the combined dispatching rules are not good enough. So in that case, we can design more sophisticated dispatching rule with reinforcement learning, and we can use that one, I think.
You say that there is some stochasticity that's been introduced at the lower level.
Yes.
Okay.
Dispatching rule level, yeah.
Okay. This can explain it.
Okay. Any other question?
Yeah, Minori Narita.
Go ahead, please. Minori.
Hi. Yeah. Thank you. Thank you for a great presentation. I have a question about page 9. Yeah. So I think so. You said that introducing imitation learning has expedited the learning process. So I was wondering, because like for some applications, like board game playing, like if you think about AlphaZero, for example, like they showed that for those domains, using domain knowledge was not needed to get a great performance. Like I was wondering, what do you think like makes also like so imitation learning has its own risk in my understanding, like it's prone to have the reward hacking and so on. So I was wondering, what do you think makes your result different from some finding from other fields, like for board game playing, for example? Like what do you think made imitation learning beneficial in this domain?
I think the main difference here is that we can actually obtain optimal solutions. I don't think there is an optimal playing strategy for a board game, right? But we can actually obtain an optimal schedule for small-sized instances for in this domain, and we can use such optimal schedules, and we can use some the states that we can observe from the optimal schedule. We can observe the job that is actually assigned in the optimal schedule. Those kind of data can be used in this case. I think that's probably the reason. Yeah.
Right. Yeah, that makes so much sense. Thank you.
Any other question? If not, so thank you very much for nice presentation and all the answers. And let me remind you that in 2 weeks, we will have a talk by Hyun-Jung Kim, and it will be about cooperative games models for scheduling problems. So looking forward to see you in 2 weeks and hope that you will make many advances in scheduling theory and practice. Till then, okay.
Okay, Hyun-Jung, thanks very much.
Thank you.
Thank you for inviting me.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye.
Panayotis,
How are you?
I'm fine.
Good.
So
Long time no see, eh?
yeah, we should start to communicate then, right?
Yes, again, yeah, we are very active, but we are working with Infineon.
Okay,
right?
I will send you an email, Panayotis.
Yes,
Okay?
yes. Long time no see.
Okay.
Hyun-Jung, I don't see many Koreans in the audience. Where is Kam Bok Lee and Young-Hoon Lee? Where is the Korean schedulers?
Yeah, it's 11 p.m. So almost 12.
okay.
Yeah. So.
Oh,
Okay,
Yes,
that
yes,
explains.
it's true, huh? It's
Yeah. What is
Thank you.
something that is interesting also is that please also take a look at the aspect of energy. We are working, our main optimization goal is energy. What Professor Pinedo proposed is, it was by chance, we proposed it 3 years ago, and due to the situation now, it is extremely important. This is the only thing they really care about. They don't care about
the energy bill, the utility bill. The utility bill is the main. That's probably in Europe more important than in Korea.
Yes, probably. But what happens is that it is they have told us that it has multiplied by a factor of 7 the cost of energy.
Yeah.
And so this is the only objective that they really care about now. Not make span is thing of the past. Forget about it. Interesting. Everyone, we are also schedulers, but they don't care. So nice meeting you, everyone. Bye.
Okay, nice seeing you. Okay.
Okay. See you in 2 weeks.
See you in 2 weeks.
Thank you. Bye bye.
See you.
Bye bye.
Bye bye, Guohua.